Hello and welcome to our next unit of study, which is thermochemistry. And thermochemistry is the study of the transfers of energy as heat that accompany chemical reactions and physical changes. So we're going to start out by talking about physical changes, and then in the second half of the unit we'll switch over to talking about chemical reactions and we'll kind of tie everything together. So the first question that you might have is, what is heat? Heat is the energy transferred between samples of matter because of a difference in temperature. Now this is circular, I know, the definition of heat and the thermochemistry, but I'm hoping that I can make a little bit of sense of this. So here I have a little simulation that I want to run. So I have water and I have a block of iron. Now this simulation has included these E's to mean energy, all right? So if I remove energy from the water, the temperature goes down. So we're talking about thermal energy here, okay? And if I heat up this block of iron, as hot as it can get, now it's going to start losing some to the air, which is a little annoying, but you can see that it's just chock full of thermal energy. Now, we should know at this point that if you add something hot to water, the temperature of the water is going to increase, okay? And that is because, look at this, okay? The energy from the iron block is going into the iron, and it's raising the temperature until both of these are at about the same temperature. Now that's fascinating. All right. So we're going to make a little drawing here, and we're going to come back to it over and over again. So here's a container that has some water in it. Okay, and I'm going to start by saying here's my hot piece of metal. Okay, and we'll say it's a cylinder. It's a hot metal cylinder. All right, so the energy is going to be transferred between the hot metal cylinder and the cooler water because of a difference in temperature. Now the question is, how do you measure energy transfer? Well, that's problematic. The answer is, this is not something that you can measure directly. Okay? So you can't measure energy directly. Now, what about measuring a change in temperature? That you can track. You know that when you put that hot metal into the water is going to increase in temperature, and the metal is going to decrease in temperature. So we might be able to relate the two. So let's keep going with this. Well, my question to you then is, well, what is temperature? And hopefully you remember that temperature is a measure of the average kinetic energy, keyword there being energy, of a sample. Okay. So the amount of energy transferred as heat is usually measured in joules. Okay, and the symbol for joules is just a capital J. All right. And the joule is the SI unit of energy, and thus heat. Now there's one thing that you're going to see rather a lot in this chapter, so I want to talk about it right now. And that is the Greek letter delta. I want you to think. You've seen this Greek letter delta before, and I want you to think about what it means. So see if you can come up with that. Now a lot of you will come up with this means change. Okay? Now my next question to you then is, how do you find a change? Okay, you always find it the same way, but how do you find the change? So pause it, think about it, see if you can come up with something. Hopefully you came up with change is just a subtraction problem, right? It's the final state minus the initial state. It's always final minus initial. If you start doing initial minus final, you're going to run into problems with sign, and by sign I mean positive or negative. So it's always final minus initial. All right, so moving along. What factors might influence the amount of energy that's transferred of heat. I want you to think back to the example we had, okay? The example we had here with our hot cylinder and the cup of water. What factors would affect how much energy gets transferred between these two things? Okay, so pause it, have a think, and see what you can come up with. Welcome back. So, a lot of people will come up with the mass of the material changing temperature. Okay, if you increase the amount of the if you went from like one metal slug to two metal slugs, you would expect a bigger quantity of heat to be transferred. All right. Now, another thing you might come up with is the size of the temperature change. So, if your hot, quote unquote, hot metal is at 23 degrees and your water is at 22 degrees, you wouldn't expect a large quantity of energy to be exchanged. And then the last thing that you probably came up with, maybe didn't say the same way, is nature of the material or identity of the material. So if you added in, let's see, if you had like hot rubber, that might not transfer as much energy as hot iron. Okay, so let's keep all these things in mind, and we're going to start coming up with some equations. All right, now this is what we're talking about here, the nature of the material. If we just want to compare the ability of a material to transmit heat, we talk about specific heat. You'll also see this as specific heat capacity, okay? And specific heat is the amount of energy required to raise the temperature of 1 gram of a substance by 1 Celsius degree. All right? Now, heat has the symbol Q. All right? So Q is heat. So the specific heat, which has the symbol C with a lowercase p, or subscripted p, sorry, is defined as the amount of energy, so heat, required to raise the temperature of 1 gram of a substance by 1 Celsius degree or 1 Kelvin. All right. Now, I've kind of given this away, but hopefully you realize from the sentence that the specific heat is Q divided by the 1 gram, which is a mass, of a substance by 1 Celsius degree. Okay? And now this is a change in temperature. All right? So Cp equals Q over m delta T. Now the way that you'll usually see this is Q equals m Cp delta T. Now, one of the things that I want you to think about is units on temperature, because they do something interesting in this unit. All right? So let's talk about the transition from 1 degree Celsius to 2 degrees Celsius. I want you to tell me what delta T would be in degrees Celsius. All right, go. You're right, it's 1 degree Celsius. Now I also want you to tell me what it is in Kelvin. Oh, interesting. So I take my 2 and I add 273 to it. I take my 1 and I add 273 to it. So I get 275 and 274, and I subtract my final minus my initial, and I get, that's right, 1 Kelvin. The Kelvin and the Celsius scale are set up so that the increments are the same size, which means in this unit, when we're talking about changes in temperature, it doesn't matter if we're in degrees Celsius or in Kelvin, just as long as we're consistent throughout. All right, now let's take a look at units. All right, let's talk about units for specific heat. Now we know that Q, heat, has a unit of joule. And we know that mass has a unit of either kilograms, or the scale that we're going to use is going to be grams. And then delta T is going to be degrees Celsius, or joules over grams times Kelvin. Haha. All right, so the unit for specific heat is kind of a mess. We'll just kind of keep that in mind as we go along. All right, the next thing that I want to do is I want to show you, this is a table from your textbook that has a bunch of specific heats of common substances. I want you to pause, I want you to look at this, and I want you to see what you notice. You're going to come up with some things, and they'll be interesting things. So pause it and think. Now the first thing that you're going to notice is that I've got 3 waters here with 3 different values. Uh-oh. So what we can tell from this is that states of matter matter. Ha ha ha. Oh, I'm hilarious. States of matter matter. You keep on asking me this, and yes, now states of matter matter. All right? Now the other thing that you're going to think about is, look at this. The specific heat of liquid water is very, very high. Now that's interesting, okay? That is interesting. So water, it turns out, is going to be really important in the study of thermodynamics because of this very high specific heat. All right? All right, moving along. Let's get to some problems. Okay? All right. Determine the specific heat of a material if a 35-gram sample absorbed 96 joules as it was heated from 293 K to 313 K. All right, so this is heat. So it's Q equals mCp delta T. Now, by the way, this equation is going to be on the equation sheet. That's something you should know, all right? And I'm asked to find specific heat. I'm given the mass. I'm given the heat, okay? It absorbs 96 joules. This is going to be the heat. So I have that. I'm trying to find specific heat. And I have a initial and final temperature. So I have that. All right. So I'm going to rearrange. I'm going to take Cp, mCp delta T, and divide by m delta T, both sides by m delta T. All right, and that's going to isolate the variable that I'm looking for, Cp equals Q over m delta T. All right, and Q is 96 joules over m, which is 35 grams, times the specific, the change in temperature. It was heated from 293, which is the initial, to 313. That's my final. So that's 313 Kelvin minus 293 Kelvin. All right, and when I do my calculations, notice I'm going to have 2 sig figs in my answer, and that's going to be 0.14 joules over grams times Kelvin. All right, it doesn't really matter if we use joules over grams times Kelvin or joules over grams degrees Celsius.